Hello and welcome to our discussion of soil consolidation. Having discussed the basics and fundamentals of consolidation in our previous lectures, today we are going to focus on consolidation settlements and see how consolidation settlements in soil can be evaluated. To start with, let's have a quick overview of what we discussed in our previous class. We talked about the E versus log P graph, and we had a look at the significance of this graph in determining the magnitude of consolidation settlement. We discussed that when we plot a graph between E versus log of P, log of pressure on the x-axis, the typical shape of the graph appears something like this. Now, this graph has different components. This straight line or a nearly straight line represents the virgin compression line. What it means is that when we start compressing the soil, if the load we are applying is if it is the first time in the entire history of the soil sample that this much load has been applied on the soil, so it will show a nearly straight line behavior. However, and this is known as the virgin compression line. The slope of this line represents the compression index. However, after applying this load, if we unload the soil sample, the the swelling of the soil sample upon unloading. So you see, when I'm unloading the sample which was initially being compressed because of the application of this load, now the same soil, when I will unload it, it will try to expand. The expansion of the soil sample is not the same. It is not equal to the compression. It means that if on a certain soil sample, I place 100 kilopascals of load, and upon placing 100 kilopascals of load, the settlement in the soil was, let's suppose, 10 millimeters. And if I remove the same 100 kilopascals load, the expansion in the same sample, the soil will expand, but the expansion will not be equal to 10 millimeters. Rather, it might be equal to 3 millimeters. So it means that when you apply the load, there is more compression, but when you remove the same load, there is less expansion. This is why this green line has a gentle slope compared to this black line here. So the slope of this line, which is known as a rebound curve, is called as the recompression index. And it is called recompression index because if we start reloading the same soil sample again, it will follow the same path over here. However, when it will reach this point, which is the maximum load that the soil has sustained in its history, it will start following the path as a virgin compression path. Let me just quickly draw it here for your convenience. So we first of all increase the load, reach this point, and from this, first of all, we increase the load, we reach this point. And from this point, we unloaded the soil sample and we unloaded the sample, there was some expansion. And now if I again start applying the load, so previously what was the maximum load or the maximum stress we had applied? Let's suppose we had applied 100 kilopascal stress. So now I again start applying the stress, I again start increasing the load. Upon reloading, I will follow the same path. So the compression upon application of 100 kilopascals again will be the same as was the expansion uh, of in the soil sample when we unloaded this. However, when we have reached this point, now the soil will start following the same path of the virgin compression line and it will start moving in this direction. So this will be the reloading path up till this point, and beyond this point, the reloading path will go like this. So this is how the soil behaves. Another important aspect to notice here is that the significance of this load, the significance of this load is really important in case of soil mechanics. Now, this load is what we call as the pre-consolidation pressure. Now, this pre-consolidation pressure, represented by sigma p dash, is something which represents that this was the load which was previously applied on the soil sample. So first of all, we apply, let me just start it once again for clarification. So first of all, we were here at this point, we apply 100 kilopascals of load on the soil. And when we apply 100 kilopascals, there was, let's suppose, 10 millimeter of settlement. Then you unloaded the soil, you removed that 100 kilopascals, and when you remove that 100 kilopascals, the recovery or the expansion in soil was only 3 millimeters. So 100 kilopascals applied, 10 millimeter settlement, 100 kilopascals removed, only 3 millimeter expansion. Now, when you load the sample once again, if you apply once again 100 kilopascals, there will not be 10 millimeter settlement. Rather, it will be only 3 millimeter settlement this time. Now, this is the fine point, and this is the important point. Initially, when you applied 100 kilopascals, there was 10 millimeter settlement. But now, when you are here on the stress path and you applied 100 kilopascals, there is only 3 millimeters of settlement. So this is why this time there is only 3 millimeters of settlement, because this 100 kilopascals of load which you are applying, the same load was previously experienced by the soil sample once in its loading history. So when your applied load is less than the pre-consolidation pressure, what is pre-consolidation pressure? Pre-consolidation pressure is the maximum pressure that has ever been experienced by the soil sample in its entire history. So you see, this 100 kilopascals, let's suppose, is the pre-consolidation pressure here. And why this is called pre-consolidation pressure? Because this pressure was experienced by the soil previously in its history. So when you apply the load, which is lesser than the pre-consolidation pressure, means when there was more load that was applied on the soil previously in its past, the soil is said to be over-consolidated. So in this zone, the soil will be called as an over-consolidated soil. This is something that we discussed in detail in our last lecture. So when the present overburden pressure on the soil is less than the pre-consolidation pressure, the soil is called as the over-consolidated soil. However, if your load exceeds this point, the soil start behaving like a normally consolidated soil. That is the first time this much load has been applied on the soil. So this is all that we discussed last time. In the same way, we discussed the definition of pre-consolidation pressure, which is the maximum effective stress that has ever been experienced by the soil in its past. That is shown by a kink in this E log P graph. And then we, based upon the same thing, we also discussed about the over-consolidation ratio, and we talked about how the over-consolidation ratio for normally consolidated soils is generally 1. For over-consolidated soils, how it is greater than 1, and for under-consolidated soils, how this over-consolidation ratio is less than 1. So this is a quick overview of what we discussed during our last discussion. So let's move to our today's goal, which is the determination of settlement in real field conditions. So what has always been our objective for these consolidation studies is to see how can we determine the settlements in the soil. So this is our ultimate goal. So let us assume a saturated clay soil in the field. Now remember, this is the field scenario that we are talking about. Imagine we have a saturated clay soil, water table is at the ground surface. So if the water table is at the ground surface, all this clay layer is fully saturated. If this clay layer is fully saturated, let's talk about a few more things. Let's say the thickness of the clay layer is H naught. Let's call it as the height or the initial height of the clay layer. And this clay layer has a certain void ratio, which we call as E naught. Let's call E naught as the initial void ratio. And we are talking, since consolidation is a time dependent phenomenon, so we are talking about the start of our test or the initial conditions. We are talking about the initial conditions. Now, on this soil, what we do is we start building a structure on top of it. Let's suppose we start building a house over here, and when we start building something on top of it, basically we are applying a load on our soil. What will happen when we'll apply certain stress on our soil? Because of the application of this stress, the soil will get compressed. You see, the soil will get compressed, and there will be certain settlement in the soil. So this settlement, let me represent this settlement as delta H. This is the settlement in the soil because of the application of the additional stress, that is delta sigma. What do you think? The height has changed from H naught to there is a small change in height. What do you think will happen to the void ratio? If I want to determine the void ratio of the new void ratio of this soil, can I determine the how can I determine the void ratio? Obviously, the void ratio of this one would be the initial void ratio minus change in void ratio. So this is how I can determine the change in void, the void ratio after the application of load, after the settlement has occurred. So with this background, if I want to determine the strain in the soil, now this is the total settlement that we are talking about, but let's see how can we determine the strain in the soil. So for the determination of strain in the soil, it is very simple. Average vertical strain, let's call it epsilon F, F subscript to represent the field conditions. So average vertical strain in the field is change in height divided by the original or the initial height. This is how we can determine the strain in the field. So this is the scenario, how it will occur in the field. But what will happen in the lab? Let's look at the contemporary lab conditions as well. When we're talking about lab, we're talking about consolidation test. And in a consolidation test, we know we perform consolidation test on a fully saturated sample. If this sample is fully saturated, it means there is a solid phase and there is a water phase. There is no air phase in this. So because it is a fully saturated soil sample. Now for this fully saturated soil samples, let's see how we can determine the initial conditions of the soil sample. For the determination of initial conditions of the soil sample, let us assume that the volume of the soil solids is 1. Let's assume the volume of the soil solids is 1. If the volume of soil solids is 1, can I say that the volume of the voids is equal to volume of water? So the volume of voids would be equal to volume of water then. So if with this basic understanding, how can we determine the void ratio? What will be the void ratio in this case? So void ratio by definition is volume of voids divided by volume of soil solids. So I can write void ratio as VV over 1. Or I can write that VV equals E naught. From this basic definition, I can write VV equals E naught, or the initial void ratio. So this was the initial conditions at time 0. What will happen long time after application of the load? Once we have applied the load for long duration of time, obviously the soil sample would settle a little bit. And we know from our basic definition of consolidation that what happens in consolidation is that there is no change in the soil solids. Volume of soil solids does not change. There is only change in volume of water. Water gets expelled through the soil during consolidation. So volume of water would get reduced. How can we determine the change in the void ratio? Can we say that this height change is equal to change in the void ratio? Obviously, from this definition, we can easily say that this change in height is actually equal to change in the void ratio. Now, with these things said, can we determine the strain in the soil sample? You remember in the field conditions previously, we tried determining ultimately the strain in the soil. So let's try and determine the strain in the soil. How can we determine strain? Strain is change in something divided by the original thing. So by using the same principle, we can determine average vertical strain in the lab, epsilon L for the lab, as change in void ratio divided by the original void ratio or the original height of the sample. So by this, we can determine average vertical strain in the lab. So this is a summary of what we have discussed so far. In the field conditions, we can determine the average vertical strain as delta H over H naught. And in the laboratory conditions, we can determine average vertical strain as delta E over 1 plus E naught. Now, in the field, we have a huge soil with us. In the laboratory, we are trying to replicate the same thing on a small scale here. And one other important thing that we have done is that in the laboratory, when we perform this experiment, we take an undisturbed sample from here and we subject that undisturbed sample to laboratory consolidation test. Now, if the sample is really undisturbed, if our assumption is true and the sample is really undisturbed, it means when I apply 100 kilopascals of stress in the field, and when I apply the same 100 kilopascals of stress in the lab, the strains in both cases should be the same. So if we have an undisturbed soil sample, the strain in the field and strain in the laboratory must be equal. I cannot say this that height should be the same, because height will not be the same. Over here we have huge soil spanning several meters, and this sample is maybe 2 centimeters in height. So delta H cannot be the same, neither can delta E be the same. However, what can be the same is the strain in both cases, which can be same. So we can replace the values of field strain and laboratory strain from the respective equations here. So we get delta H over H naught equals delta E over 1 plus E naught. Now, our objective is to determine the settlement in the field. Our objective is to determine and tell, okay, when we are constructing this building, let's suppose if we are we're constructing a building which is applying 100 kilopascals of stress on our soil, how much settlement would occur? Would it be 10 millimeters, 20 millimeters, or 100 millimeters of settlement which would occur? So this is our ultimate goal. So if our objective is to determine the magnitude of settlement, so isn't this delta H representing the magnitude of settlement that can occur in the soil? So from this equation, our ultimate goal is to determine the value of delta H. So what I can do is I can rearrange this equation, and by rearranging this equation, I can write it like this: delta H equals H naught in times delta E over E naught, 1 plus E naught. And this delta H I can also call as S subscript C, which represents consolidation settlement in the field, which is my ultimate goal. So it means simply by using this simple equation, I can determine the consolidation settlement in the soil. Now, you see, what can I do if I want to determine the consolidation settlement in the soil? All I need is I need to know H naught. What was the initial thickness of the clay layer? That we can determine by looking at the borehole data and the geotechnical investigations data. We can determine this. This delta E is something that I can get from the laboratory. However, this is something which we will discuss more in our coming slides. And E naught is something we can also get from our laboratory testing. So some information we are getting from the field, some information we are getting from the laboratory, and finally by using it we can determine consolidation settlement. Now, when we want to determine the settlements, there are basically two different ways by which we can determine consolidation. One is by using MV. If you remember, while talking about while talking about deformation versus pressure plot, I told you about the compression index and some other indices, and I also talked about MV. So there is a simple relationship by using which we can, if we can make use of MV and determine consolidation settlement. And this equation goes consolidation settlement equals MV times delta sigma. Delta sigma is the additional load that we are applying times height, or the initial height of the soil layer. So by using this simple equation, we can determine consolidation settlement. And we know MV equals AV over 1 plus E naught. This is something that we have discussed earlier in one of our earlier lectures. And in the same way, there is another approach by using which we can determine consolidation settlement. And this is by using E versus log P graph. And from this, consolidation settlement equals H times delta E over 1 plus E naught. Now, this is the equation that we have derived on the previous slide. Now, these two methods are very frequently used worldwide for the determination of consolidation settlement. For the matter of this coursework, we will mostly be focusing on this lecture, on this method of determining consolidation settlement. So we will mainly be determining consolidation settlement by using this method. And I hope if you can learn how to determine consolidation settlement by using this method, determining consolidation by using this method won't be much difficult for you. So let's see how can we determine this consolidation settlement. And when we want to determine consolidation settlement by using this method, you can well understand that this H, as I explained on the previous slide, is the height of this layer. This is something we get from geotechnical investigations. E naught, which is the initial void ratio, is again something that is not very difficult to determine and is obtained from the laboratory consolidation test. The real difficult thing to determine is delta E, how to determine the change in void ratio upon application of certain stress. That is something which is a little tricky, and this is what we are going to discuss in the rest of this lecture. So for the determination of delta E, there are three different cases that we will discuss. First of all is case of a normally consolidated soil. Now this expression represents a normally consolidated soil. What is a normally consolidated soil? Where the present overburden pressure is greater or almost equal to pre-consolidation pressure. However, this is less than the final applied stress. So this is what we call as a normally consolidated soil. What this expression means is going to be further explained by means of the graph that I'm going to show here. So let's look at a typical E versus P graph for a normally consolidated soil. Now this is the E versus log of P graph, where y-axis represents the void ratio and x-axis represents the log of the applied stress. If we are talking about normally consolidated soil, you know normally consolidated soil, the entire loading path is along the virgin compression line. This is where the entire loading path would act. Now the slope of this line is what we have already discussed many times, is compression index. The slope of this line is compression index. And this point, which is often of our interest, is what we call as the pre-consolidation pressure. This is what pre-consolidation pressure, the maximum pressure that the soil has experienced in its past. So if our soil is normally consolidated, for a normally consolidated soil, we know that our current stress level, our current applied pressure is going to be almost equal or a little greater than the pre-consolidation pressure. So our current applied pressure has to be greater than the pre-consolidation pressure. So it means our current stress level should be on the right side of this line. So this point can probably represent our initial stress conditions. And our initial stress conditions can be represented by sigma V naught prime. Pre-consolidation pressure represented by sigma P dash to represent the effective stress, and our current or the present effective overburden pressure can be represented by sigma V naught dash. So let's say our initial pressure or the current pressure that is experienced by the soil in the field is sigma V naught prime, and the corresponding void ratio is what we call as E naught. Now, we start applying load on our soil. Now, if we start applying load on our soil, what will happen to the stress level? If we increase the load, if we increase the stress, it means the stress is increasing towards the right. It means we will reach somewhere this point, which is the final, going to be the final stress level. Isn't this what we do in case of a consolidation test? We first apply certain initial load, and when we increase the initial load, we move towards the right. We our pressure or the applied stress keep on increasing, and our void ratio keep on decreasing. So we will reach around this point. Let's see. So this is our final stress level. Now, if we know the initial stress and if we know the final stress, can we determine delta E from this? Obviously, we can easily determine if we have plotted it on a graph, we can easily determine delta E from this one. And in the same way, this final stress level can also be determined. How can we determine this final stress level? This final stress level would be equal to this initial stress level plus the change in stress. This final stress level would be equal to the initial stress plus delta sigma, the additional stress that we have applied on our soil. So if you can understand this figure, the rest of the things would become very easy for you. So that's why I'm trying to explain it a little bit more in detail. Okay, so now this figure explains our case for a normally consolidated soil. Now, if you can understand this, from this we can easily determine the compression index. If I ask you what is compression index, you would tell me compression index is the slope of the virgin compression line. Okay, what is the slope of virgin compression line in this case? The slope of compression the slope of this virgin compression line would be this ordinate or the y-axis value divided by the x-axis value, which can be written something like this. So Cc equals this delta E. Delta E is this y-axis value between the initial and the final divided by the corresponding x-axis value, which is sigma V naught plus delta sigma divided by sigma V naught prime. Because, because this is all plotted on a log scale, because it is plotted on a log scale, you remember this x-axis is on a log scale. So this is why I can convert it as into a fraction. Otherwise, it would have been log sigma V naught prime plus delta sigma minus log of sigma V naught prime. So because both of the terms would be log, that's why I can write them as a fraction. So what I can do is, what I want to determine is, I'm more interested in determining this delta E. Now, if I want to determine delta E, it means I can take all this thing in the denominator and move it on the right side. This is what I've done here. So delta E with all the denominator thing moved on the right side, it becomes Cc times log of sigma V naught prime plus delta sigma divided by sigma V naught prime. Now, this delta E is what I told you on the previous slide is what is important for me. When I am calculating consolidation settlement, this is the basic equation of consolidation settlement. And in this basic equation of consolidation settlement, what was what was missing? I told in the previous slide that it is very easy for me to determine H. It is quite easy for me to determine E naught. However, this delta E is something which is difficult for me to determine. So this delta E I can easily determine by using this equation. So what I can do is I can replace the value of delta E in this equation. And if I put all this in this equation here, I can come up with the following equation, where this consolidation settlement, which is my ultimate goal is to determine consolidation settlement, in where consolidation settlement equals H times Cc over 1 plus E naught times this log thing here. So I've simply replaced the value of delta E over here and I've got this equation. So it means if it is a case of a normally consolidated soil, for a normally consolidated soil, I can determine the consolidation settlement by using this equation very easily. Now, this equation looks complicated, but if you understand the process, what is going on here, you don't need to cram this equation. Rather, you can easily write down this equation from your understanding. So this was the case for a normally consolidated soil. What happens if we have an over-consolidated soil? Now, if my soil is over-consolidated, for an over-consolidated soil, it means that the present overburden pressure is less than not only the final pressure but also the pre-consolidation pressure. Both the present and the final stress level is less than the pre-consolidation pressure. What I mean by this is, let's try to explain it by means of the graph we draw. This is the consolidation graph, where we know this is the virgin compression line, and this point represents the pre-consolidation pressure. The slope of this line we call as the compression index. The slope of this line we call as the recompression index. So what I mean by this is, if the soil is over consolidated, it means that from the definition of over-consolidated soil, we have already studied this thing, that a over-consolidated soil is the one in which the present effective stress is less than the past pressure that has been experienced by the soil. So it means the present effective stress should be on this side of the graph or on this side of the graph. Because it is an over-consolidated soil, so the present effective stress should be on the left side of the graph somewhere over here. So this is the present effective stress on the soil. Now, if this is the present effective stress on the soil, we can call it sigma V naught prime. We can determine the void ratio. Now, once we apply this stress, and we reach the final stress. So for example, we started construction of the house, and this is when all the load of the house has been put on the soil, and we are at this stage. So if you notice the change in the void ratio that has occurred, all the void ratio change has occurred in this zone, which is the over consolidated zone. If all the change has occurred in this over consolidated zone, it means in our calculations, do I need to use this CC, or this time should I use this CR instead? It is obvious that because our zone of interest is lying in the over consolidated zone, because our soil is over consolidated right from the beginning till the end, this is why we should not be using CC in our calculations. Rather, we should be using CR, the recompression index, in our calculations. So let's see how we can use CR, or the recompression index, in our calculations in case of an over consolidated soil. So for the final for the final stress level, we can again write the final stress as the initial stress plus delta sigma. So the applied stress, the additional stress that has been applied. Now, in the it's very similar to the previous slide for a normally consolidated case, we can try to write down the equation for this zone. Now, if I try to write down the equation for this zone, I can write the equation for this zone as from the definition of recompression index. Now, recompression index is simply the slope of this line, means y over x. This is what I need to write down. And this is how I can write down y delta E over x, which is the difference between this value and this value. But because both are on the log scale, so we'll write sigma v naught prime plus delta sigma from here and divide it with sigma v naught prime from here. Again, since our objective is determination of delta E, so I can rearrange this whole equation. I can take this denominator term on the right side and I can rearrange and write it like this. Now, if you look closely, this equation is exactly the same as the equation that you have derived on the previous slide for a normally consolidated soil. The only difference is that C instead of CR here, there was CC over there. So we use compression index in that case when we were using a normally consolidated soil. So what is our ultimate objective? Our ultimate objective is to determine the consolidation settlement. And if we want to determine the consolidation settlement, we have to insert this value of delta E in the basic consolidation equation that we have derived earlier. And when we replace this whole equation over here, we come up with this final equation of consolidation settlement. So this tells us that if our soil is an over-consolidated soil, and how will we know that our soil is over-consolidated? We will know that our soil is over-consolidated by looking at this criteria. If our initial stress and the final stress both are less than the pre-consolidation pressure, then we can easily determine the consolidation settlement by using this expression. And in this expression, H is the total height of the soil in the field, CR is the recompression index, E naught is the initial void ratio that you can determine from the consolidation test. CR can in fact easily be determined from this graph, from the slope of this graph. Sigma VF is the final stress level and sigma V naught prime is the initial stress level. So this is how we can solve the case for over-consolidated soil. Now finally, there is a third case of an over-consolidated soil. Now this is quite an interesting case. If you compare it, if you look at the previous one, here what happened was that your initial stress was less than the pre-consolidation pressure. But when you increase the stress, the final stress was also less than the pre-consolidation pressure. It means all the consolidation settlement occurred in the over-consolidation zone. But isn't it possible that when you apply your applied load is so high that it can overshoot this pre-consolidation pressure and start falling in this zone? In that case, what will happen is, in this case, your pre-consolidation pressure is greater than the final pressure and the initial pressure. Pre-consolidation pressure is greater than the final pressure and the initial pressure. But in the other case, it is possible that the final pressure can be larger than the pre-consolidation pressure and the initial overburden pressure. This is the case that we are going to discuss on the next slide. So you see here that the final pressure is greater than the pre-consolidation pressure and the initial pressure. So how can we solve this case? Now, in order to solve this case, again, we'll do the same thing as we have done before. We know we have already set up all these things earlier. This is our initial stress and the initial void ratio. Now let's start applying the load, and it is possible that our final load comes in this zone. Now, if our final load comes in this zone, how can we determine the consolidation settlement in this case? So again, this is delta E. The final stress is again going to be the similar equation. It will be equal to initial stress plus delta sigma. But how can now we determine this delta E? Previously, it was easy to determine delta E because either we were in this zone only or we were in this zone only. But how can we determine delta E now when our applied stress is extending in two different zones? It is very easy to determine delta E. What we can do is we can determine delta E for this zone separately by using the same technique that we have used in the previous slides. And we can again determine delta E for this zone separately by using again the same philosophy used in the previous slide. So we determine delta E in this zone, let's call it E1, and we call it E2, and add these two up, and we can determine total delta E. How we can do this is by using this equation. So you see what we have done here is, first of all, we can determine the slope of this part, this initial part. The slope of this part would be the recompression index. The slope of this part would be the recompression index, and recompression index between initial pressure and pre-consolidation pressure. Initial pressure and the pre-consolidation pressure. So this first part represents the slope of this zone, this first zone. But when we talk about the second zone, the slope of this part would be the slope between sigma P and sigma VF. So you see, for the second part, we have sigma VF and sigma P. So this is how we can determine delta E for this case. And once you have determined delta E, the rest of the procedure is simple. You simply insert it in this basic equation of consolidation. And when you put it in this basic equation of consolidation, you get the final consolidation equation given like this. Now, I would suggest all of you to try deriving all these equations by yourself, by your hand, and unless you do that, it will be very difficult for you to actually understand these things. So unless you write them by yourself, it will always look alienated and difficult to you. So I strongly suggest you guys to draw these graphs and try deriving these equations by yourself. So this is simply by using these equations, we can easily determine consolidation settlement. So finally, there is a quick summary of all the formulae that we have derived so far. What I've done is I have simply summarized all the expressions that we have used or will be using on a single slide. So by using these expressions, we will be trying to solve some numericals on coming slides or in the coming lectures. So a couple of expressions here which we have not derived earlier. You should remember these relationships. Now, in many times we do not have compression index information with us, and if you do not have compression index information with you, you can determine compression index by using the liquid limit of the soil. So this is an empirical expression given long time ago by Terzaghi, in fact, but it is still used today in professional practice to have an initial estimate of consolidation of soil. So you can determine compression index by using this expression. And if you have the value of compression index and you want to determine the recompression index, you can simply take 10% of compression index as the recompression index. So these are the two expressions that probably we have not discussed earlier. Rest is everything that we have already discussed. So I've just summarized them here for your convenience. So that's all for the day. Thank you very much.